opportunity to speak here. So, today I want to speak about non-commutative deformations. This is joint work with Michael Weems, which we began together in Edinburgh. Michael is now in Glasgow. So I should speak for 50 minutes?
Yeah.
Yeah. Thank you. So, I'll start with an example. I'll say more about the example later on, but to give you an idea of the geometries that we'll be interested in. Is something I can point with? No, okay. So I'll just point. So start with...
Maybe this one has a pointer, I'm not sure, but you can try.
Let me try.
Maybe. No?
Okay.
Maybe not.
I don't think so. It's okay.
That's okay.
Please ask if things are not so clear. So let me start with this quotient singularity. So we have the cyclic group on 3 elements, acting on C2 by complex rotations. Take the quotient of that, get a Kleinian singularity, which has a resolution you've probably seen before, by replacing that singularity with a pair of projective lines intersecting at a point. So that's a surface. And if I take a generic perturbation of that surface, that gives me a 1-parameter family of surfaces, a threefold, which I've drawn in the middle, say X, and that contains 2 projective lines. And in that threefold, as in the surface, these projective lines are rigid. However, they deform non-commutatively over an algebra A. So I'll explain what that means, and then I'll give some applications. So there's applications to enumerative invariants. I won't speak about those today. There's applications to what I'm calling here the local geometry of X. I'll explain that. And if you are interested, I will briefly say how this applies to give symmetries of the derived category of X. This was in some way our original motivation. But actually, yeah, this work has grown beyond that. But I'll state that. Okay, so let me get started. Now, so this formalism of non-commutative deformations follows work of Kawamata. Let's take a finite collection of coherent sheaves on X, our variety, and I will say they're a simple collection if they are pairwise orthogonal and each one has only scalar endomorphisms. So for instance, let's take the structure sheaves on these 2 curves, consider them as torsion sheaves on the threefold, and then those are pairwise orthogonal because they are torsion, and they have scalar endomorphisms because they are compact. So this is an example, EA and EB, and in general, given a finite set of E's, the construction of the non-commutative deformation of those, I'll explain why I'm calling it that, but for now I'm just going to construct it, is first by taking the direct sum of those sheaves, and then by universally extending that by as many copies of these E's as I can extend by. So the universal non-trivial extension by the EI's gives me F1 from F0, likewise F2 from F1, and so on. And this process may not terminate, but in any case I take the limit of those Fi's. And this is a non-commutative deformation of the e's. Next, I'll give an example, then I'll explain why you should think of it as the non-commutative deformation. So first, a simple example where it gives us nothing new. That's to take C2 now modulo the cyclic group on 2 elements, again declining in singularity with a resolution by 1 projective line, and I can again take a perturbation of that and form a 1-parameter family, a 3-fold, and I want to take this non-generic perturbation. W is the coordinate of the 1-parameter family, and so what I've written here, of course, is xy equals z squared, the equation of the singularity, and perturbing it by adding this w gives me a new 3-fold singularity, and x is a resolution of that 3-fold singularity. So now we have a single projective line, and it has an infinitesimal deformation in the w direction, which is kth order, depending on the power of w there. And in this situation, if I start with just a single sheaf, E, the structure sheaf on C, considered as a sheaf on the 3-fold X, then that has a single non-trivial extension. So I start with F0, and that non-trivial extension I denote by F1. And then the next step, I can extend that by E to give F2. But if k equals 2, as in this example, then the process stops. So F2 has no non-trivial extension by E. So that's my F, the limit is F, that is my non-commutative deformation, except in this case you can see it gives nothing new. This is just commutative, this example. But now let me go back to the original example and we'll see that it does give something new. So, on the left, the resolution of that quotient singularity. The equation of the singularity is xy equals z cubed, and I add the last monomial zw squared to give a generic deformation of this surface singularity. And now that has a resolution with these 2 projective lines, CA and CB. And let's write EA and EB for the structure sheaves on those, considered as torsion sheaves on X. And now they have mutual extensions going one way and the other, corresponding, if you do the calculation, to that intersection point between the curves. And then I form my non-commutative deformation. So F0 is the sum of EA plus EB, and the universal extension of that is extending EA by EB and EB by EA. So I've written it down at the bottom, that gives me my F1. I can extend that by EA and EB the other way around. That gives me my F2, and then it's a calculation that F2 has no non-trivial extensions by EA or EB, so that's my F. So this you should think of as the non-commutative deformation of the EA and EB, and let me start to make that precise now. Okay, so F is the pro-representing hull for the non-commutative deformation functor of these EIs. So I'm not going to explain the term pro-representing hull. I will explain what the non-commutative deformation functor is. So that functor will control the non-commutative deformations of the EIs. And what's a pro-representing hull? It's as close as we can expect to a universal object for this non-commutative deformation functor in general. So I won't give more details about that because actually we'll restrict to a scenario that includes these examples where this functor is actually representable. So we won't be working in this more general setting. And now, given this f, I can just take endomorphisms of it as a sheaf on X. So that gives me an algebra. And I want you to think of this as the algebra of deformations of the sheaves I started with. And this may be non-commutative. Notice also that it has the structure of an algebra over Cn, where n is the number of sheaves I started with. That's because f had a direct sum structure. So in the first example, that algebra is just the truncated polynomial ring, depending on the order of the deformation. So if k equals 1, it's a first order deformation, that's just the dual numbers. So it's what you'd expect. It's commutative, but in the case of the two curves, it's this C2 algebra, which I've written, I hope it's visible to everyone at the bottom. So that algebra has two idempotents. They correspond to the C's on the diagonal, and it has elements corresponding to the anti-diagonal T's, which map one part of the direct sum to the other, and vice versa. And so those elements, what this matrix notation is saying is if you compose them the right way round, you'll get one of the T squares on the diagonal. So that's what this notation means. It's a 6-dimensional algebra. T cubed is 0, so there's nothing more than those 6 one-dimensional subspaces I've written there. And I want you to think of this as the non-commutative deformation algebra, but what does that mean? So in the commutative case, we could take spec of this Artinian ring, and oh, okay,
It's the computer. No, it's back.
it's back. Okay, okay, so that woke everyone up. Thank you. You can take spec of this Artinian ring, and I'll show on the next slide how you can write down a deformation functor using that. But of course, we don't want to take spec of this. But I'll show you how you can make sense of a family of sheaves over this algebra. And that's in fact not so difficult. It's just a change of point of view on the usual deformation theory. Okay. No questions at that point? Okay. So a reminder of the commutative classical deformation functor formalism. So I start with a coherent sheaf on X, say E, and C-def, the functor of commutative deformations, takes me from bases of commutative deformations to the set of families over that base, which deform my E. So I hope this is familiar to most people. So I start with an algebra describing my base. So I want that to be Artinian and augmented. So augmented just means there's an algebra morphism to the field C. So you should think of that as specifying a point in spec B. And it's a commutative C algebra for the moment. So then, what is the set of families deforming E over that base? Well, I take F, a coherent sheaf on X times spec B, and I ask for that to be flat over spec B. And I also ask for it to restrict to E, by which I mean that F should restrict to E at the point in spec B that we've picked out. Right, okay, yeah, so if I restrict f to x times the point, that should be isomorphic to E. And I take these up to a suitable equivalence relation, which I don't speak about. So now I just want to change the viewpoint on this a little bit to put it in a form that will generalize to the non-commutative world. And that's not so hard. All I do is I take my f coherent sheaf on x times spec b. Now that has a projection to x, and I can push down f via that projection. And now because spec b is affine, I don't lose much information by doing that pushdown. So I get a coherent sheaf on f, and because it was pushed down from, a coherent sheaf on x, and because it was pushed down from x times spec b, the pushdown has the structure of a B module. So I think that's on the next slide. So I reuse the notation f for the pushdown. So that's a coherent sheaf on x, but it also has the structure of a B module. And previously I asked for some flatness condition, but actually because B is Artinian, it's equivalent to just ask for this to be a free B module. So I have f, a free B module in coherent sheaves on x, and this last condition is just saying restricts to E. So this is rephrasing that. So f is a B module, and I just tensor over C, tensor with C over B. That's C with the B module structure coming from the augmentation. And the condition that f restricts to E over the central fiber just becomes that tensor is E. Okay, so now, in this form, it's a formal observation to say that this generalizes to, a non-commutative deformation functor where I take a finite family of coherent sheaves E1 to En, and then I can write def n, the deformation functor of these E, to go from art n, which is now still Artinian, still augmented, but Cn algebras. And I don't require that they're commutative anymore. So now I have a morphism from B to Cn. So you should think of that roughly as picking out n points in this non-commutative space. And what does it mean to have a family over this non-commutative space? Well, we don't have to make sense of what that means. We can just say exactly the same thing again, that we take free B modules in coherent sheaves on X, and the restriction condition is now tensoring with Cn and getting back the direct sum of the EIs. So this is what I mean by the non-commutative deformation functor. So in general, this is pro-representable or has a pro-representable hull, but now I give a situation where it's in fact representable. Yeah. So, okay. So this setting generalizes, well, it includes the examples I had at the beginning and many more. So I take a threefold Y with a single isolated singularity at some point P as a rational singularity by assumption, and I take a resolution X with exceptional locus assumed just a curve. So the dimension of the exceptional locus is 1. And because P is a rational singularity, it follows that that this exceptional locus is actually a tree of projective lines, C1 to Cn. And as before, I take the structure sheaf on these Cs, and for convenience later I'm going to twist by -1. So those are the EIs that I'll deform. So this is a contraction of three folds. This includes flopping contractions, and I'll talk about those later. And yeah, this is the first of a number of theorems along these lines. We'll be able to make more general statements in more general geometries, but I want to start with this. This is the first result along these lines that we proved, that the non-commutative deformation factor is representable by some A.
A is who?
A is...
What is A? Who is A?
Okay. So I don't give yet the construction, but later I will give the construction. Right.
But it's not the thing you wrote down before, like the endomorphisms of that?
Yes.
Oh, it is?
It is.
Okay.
It is. I don't want to circular at the
Sure,
moment.
sure.
But we give an explicit construction of A, and I can, assuming that, I can work in the other direction and say that I can get an F from this. So there exists an F. Now I can unambiguously say universal deformation of the EIs. So why is that? Well, if this functor is representable, what does that mean? It means that the def n that I defined before takes the form of a Hom functor in the category of Art n, of Artinian Cn algebras. It's just Homs from my representing object A. And in that case, if I look at the images of those two functors on A, so that's on the one hand deformation families over A, and on the other hand endomorphisms of A, then there's a canonical endomorphism, the identity, and that corresponds to F, my universal deformation of the EIs over this A. Okay. So I'll give an example on the next slide. I'll give the general construction later. But for now, I just want to emphasize that from this A, I get back the commutative deformations as well. So how do I do that? I take A, divide out by commutators. So if you were thinking of A as an algebra of matrices, then that makes it diagonal, and I can pick the ith element on the diagonal. So that will represent the commutative deformations in the classical sense.
In which sense do you divide by commutators? Just by subset as a linear subspace?
So so I take the
okay, so
ideal.
it's no
That's right.
ring structure. Okay.
Yes.
Yeah, you divide by linear subset of commutators. Yeah, okay. But it's not an algebra.
Sorry, so I divide by the two-sided ideal generated by commutators. Yes.
Matrix algebra is a whole thing.
So we start with a Cn algebra. We divide by the two-sided ideal of
Two-sided.
commutators. So it is still an algebra. I'm sorry.
Yeah, no, that's okay. No, just to follow it.
So in the case n equals 1, it's just, would I call this Abelianization? I'm not sure, but it's dividing by the two-sided ideal of commutators. Okay, so a more interesting example, where even for a single curve, which has commutative deformations, the non-commutative deformations are giving something new, and we'll see later why this new information is useful. So I've written down an equation of a singularity. So this is a flopping contraction, and if you know something about flopping contractions, you might know that these have a associated Dynkin type. So this is a type D4 flopping contraction. So it's the next more complicated after type A flopping contractions. And in this setting, Actually, the non-commutative deformations always give something new. So now the normal bundle of that curve is O minus 3 plus O1. And that O1 has two independent sections, which correspond to two non-trivial deformations of the curve. So green and red. And the zero of the section is fixed infinitesimally by the deformation, so that's what I'm trying to draw there. So red fixes the north pole, maybe, and green fixes the south pole. And I perform this procedure, and I get this result for A. So that's generated by x and y, which in this case anti-commute with this single relation, x squared minus y cubed. So we call this jokingly the quantum cusp. And if I do this procedure of quotienting by the two-sided ideal generated by commutators, then I just get this. So xy and the cusp relation, so that is clearly finite dimensional, and it's 5-dimensional, and in fact it's an exercise, a fun exercise, to see that this non-commutative algebra is 9-dimensional. So this is giving us a little more information about the deformations, but also recovering the commutative deformations. Okay. Let's see how I'm doing for time. So I will now accelerate a little. My apologies. So, given a singular y, as before, this may have multiple minimal resolutions. So this is the case of a flopping contraction that I've been talking about. So in that case, if I start with x to y, a flopping contraction, then there exists another x prime with a contraction to y, which is birational. And the indeterminacy locus of that birational map corresponds with the exceptional locus of the contraction on both sides. So you should think of this as taking a curve and replacing it with a different curve. And the result may be non-isomorphic as a variety. So for example, this is the first example we looked at. So if I have a single rigid projective line in a threefold, then that possesses a flop. So I can replace C with some C prime in an X prime. And similarly, if it has a single kth order deformation, this is this case, there's a flop of that as well. And the previous slide was also an example of a flop. So there are many examples of different sorts, and there's not yet a full classification. Okay, but given a flop, these spaces may be non-isomorphic, but in fact they have equivalent derived categories. So this is a theorem of Bridgeland and Chen. Chen did the singular case of this result, so I assume that the flop spaces are Gorenstein terminal, and then there exists equivalences between their derived categories, and they are induced by the birational map in the following sense, that there is this technology of Fourier-Mukai functors, which takes what's called a kernel on the product of the two spaces that I'm interested in, x and x prime, and from that produces a functor from x to x prime. And it also similarly produces a functor from x prime to x. So what's the kernel I take? I just take the fiber product of x and x prime over the base y. So I consider this as a subvariety of the product x times x prime and look at the structure sheaf on that subvariety. And this gives me a functor from x to x prime and a functor from x prime to x, which Brigand and Chen prove are equivalences. And this is where the non-commutative deformations come in. It turns out these are not inverse. So you might guess that they're inverse. They're canonical equivalences between x and x prime, but they're not inverse, and this theorem explains why. So there's a lot of derived category notation in this, but the way you should read the first line, the cone from the identity functor to this composition, is saying if you measure the difference between this composition and the identity, then the result is this. So it's Furumu Kai functor induced by this, this kernel, which I can calculate from F, the non-commutative deformation family, over the base A. So I'm not going to go into too much detail on this, but yeah. So if you're familiar, then this equation will be familiar to you, and you might also know this terminology of twist autoequivalences. And in this case, composition of the functors, x to x prime and back, is a twist by this non-commutative deformation family over the non-commutative algebra A. So, this theorem generalizes work of Toda. He covered those two examples I gave previously, where there's a single infinitesimal deformation, and in that case, the possibly non-commutative algebra is commutative. And so this more general theorem includes the non-commutative case, and it's also been now extended to families in higher dimensions, where you can have a family of flopping curves. This is work of Bozenta and Bondal. So I want to briefly say something about the potential applications to describing the geometry using this non-commutative algebra. And then I'll come back to the construction and its generalizations. So we had a conjecture that A, the non-commutative deformations of those curves in X, it should recover the complete local ring at 1. So this is true. It's quite easy to see when there's only a single deformation, when A is actually commutative. But the general hope is that it recovers in the non-commutative case. So this algebra gives a way to classify the geometries that occur here. And this has now been proved if that singularity is a quasi-homogeneous hypersurface. This is work of Hua and Toda. And in another direction, they propose that if the algebra is augmented by the structure of an A infinity algebra, so the same algebra, but making it an A infinity algebra, which means that it has massy products, so KRE products for every K potentially. In fact, it's just the even Ks that appear in this construction. And they conjectured, and now Hua has shown, that with this extra information it is possible to recover the complete local ring. So perhaps surprisingly, this is the same as studying complete local geometry on the base, but perhaps in some ways more convenient. What else to say about that? I won't say anything more about that. I'll return to that subject at the very end. Okay. So now I'm going to explain the construction of A in a slightly more general setting than before. Well, more general and less. For simplicity, let's take Y to be affine, again with rational singularities, but now not necessarily isolated. So in this picture I have a line of singularities marked Z, and again I have a contraction to this base, and I still want the dimension of the fibers to be at most 1 in this contraction. So here's a typical situation. I have a family of curves degenerating to a nodal curve, and that contracts to a line of A1 singularities with an A2 singularity in the middle. And so Z will denote the locus over which F is not an isomorphism. If I pick a point in that locus and I look at the fiber above it, that will still be a tree of projected lines. Again, call them Ci, and look at the sheaves EI associated to them. Now, then the theorem is that the non-commutative deformation factor, as before, is pro-representative. Okay. So what does that mean? It means that if I extend the Artinian category to the pro-Artinian category by taking limits, then there exists an object in that category, which when I take Homs from that, Homs from that to an Artinian ring, and that gives me the deformations over that Artinian ring. So this is natural. It's like the representing object we had before, but it doesn't need to be finite dimensional. So it can be infinite dimensional because of moving in that family, essentially. Okay. Now, this is not much of a theorem because actually this follows from general considerations. But what do we actually prove? It's something more useful. We show that there exists an OY algebra, AY, so that's in particular a sheaf on Y, but it also has an algebra structure over the structure sheaf. And that, if I complete at my point P, that gives me back the pro-representing object for a non-commutative deformation. So it puts together all the deformations of the fibers into one object, such that if I localize at P, it gives me back a non-commutative deformation algebra, but only up to Morita equivalence. That's a feature of this theory. So I forget where do we go next? Right, so now I'll define that A. This is the example that I was talking about before. So take this singularity uv equals x squared y. So that's singular along the y-axis, A1 singularities and A2 at the origin, and the resolution I've sketched as one projected line resolving the A1 singularities and 2 resolving the A2. So that's the exceptional locus. And I'll give the result of this computation for this example at the end. But let me say what the construction is. So it's a theorem of Vandenberg that there exists a vector bundle on X. The terminology is this is a tilting bundle that describes the derived category of X as a category of modules over an algebra. So this bundle will be useful to us in the construction. So what's the statement? That I have a vector bundle OX plus n, and if I look at the endomorphism algebra of that one, X, then modules over that are derived equivalent to X. So this bundle clearly catches a lot of the geometry, and A is a quotient of its endomorphism algebra. So I take the two-sided ideal generated by these particular endomorphisms. So I want psi to be an endomorphism of the bundle which factors through the structure sheaf, or the direct sum of A copies of the structure sheaf for sum A. And if I take the quotient, it gives me AY, which we call the contraction algebra, but it's the AY that appeared in that theorem. And in the case that we only have a single point in the non-isomorphism locus, if we're just contracting a curve to a point, then this AY is just supported at that point. And if you forget that it's a sheaf, then it gives the A that I was talking about at the beginning. So let me give an example. So for brevity, I've written this in the language of quivers, and partially. So the algebra has, the bundle has a summand OX, the structure sheaf, and it has two more summands by construction corresponding to the two curves in the central fiber. So this quiver represents the endomorphisms of that bundle with its three summands. So the top vertex corresponds to the structure sheaf, and the bottom two vertices correspond to the curves. Yeah, okay. So just let me explain in words what's happening in this picture. So the quiver is a directed graph. What I mean by putting that in braces and putting C, I mean the free algebra on that quiver, which is paths and multiplication given by composition of paths. So in particular, there are length 0 paths corresponding to the vertices, and those are just the projections onto those three summands. And there are other paths, some of which I've labeled, and some relations which I've not given. So, in particular, the endomorphisms of the structure sheaf on X correspond to functions on the base Y, and I've labeled the function little y as a loop on the top vertex. So that's showing how the functions on Y act on this algebra. And yeah, so you see that there's a Y on the bottom as well. That's also giving me action. And then what was my procedure to form A? I quotiented by endomorphisms that factor through some number of copies of the structure sheaf. And in the quiver picture, that just corresponds to factoring by all paths that pass through the vertex corresponding to the structure sheaf, so the top vertex. So that's all I've done to go from T to A. I've killed the top vertex and I'm left with two arrows, no relations, one of them is Y. So that's indicating the module structure of AY over the functions on the base Y. Okay, so now we can prove a theorem that the support of AY as a sheaf on Y is precisely this Z, the non-isomorphism locus. And as a corollary, if the dimension of this AY, just as algebra over C is infinite, then the dimension of the non-isomorphism locus must be positive. It can't just be a point. And so, depending on the dimension of this AY, I can detect whether this F was a divisorial contraction. And so this setup we have includes flopping contractions and divisorial contractions to a threefold. And this algebra detects which one we might be, or more precisely, if you're a divisorial contraction or not. And surprisingly, this is not true for the commutative version of that. So there exists an example, a family with a central curve that has non-commutative deformations that are infinite, but when I pass the commutative deformations, it's finite. So, so the non-commutative deformations detect the divisor in which that curve sits. So this is quite surprising. Now, okay, so I've got 5 minutes to explain the most general setting that we've proved these sorts of results in, and it's somewhat cleaner in that setting. So, right. So I don't put any assumption on the dimension now, apart from I'm a surface or higher. And I don't require that the fibers are just curves. So this picture is supposed to indicate a family of curves generically, but with some surface at a particular point. So we can handle those cases under the assumption that there is an F relative tilting bundle on X. So that's like in the theorem of Vandenberg that I stated, a relative generator for the category X over Y. And I ask for F to be Kreppen and Y to be Gorenstein. So this includes certain symplectic resolutions. So I've got an example here. It includes a large class of contractions where the fibers are curves and surfaces due to work of Toda and Uehara. Or we could just ask that the fibers are curves. In that case, we'll be using the result of Vandenberg in a slightly more general form than the previous slide. So, so the example here is the cone of singular matrices, n by n, and that has a resolution, a Kreppen resolution, by taking the space of pairs of a matrix and a hyperplane in Cn. So I just ask the image of the matrix to lie in that hyperplane. So for a generic singular matrix, the rank is n minus 1, so there's only one hyperplane containing the image. But the more singular matrices have fibers P2, P3, and so on. And the zero matrix has a fiber Pn minus 1 over it. So we'll be able to say something in this case. So what's the theorem? Now, there exists a sheaf of algebras on the base Y, curly A, and a sheaf curly F on X, such that that A has support, the non-isomorphism locus, and if I pick a point in that non-isomorphism locus where I've got a curve over it, then in that case at least these objects control the non-commutative deformations. So what do I mean by that? I'll say here. And now on the next slide, I'll give an application of these objects to autoequivalences of X, which is the reason for thinking of them as natural objects. But in this case where the fibre is a curve over the point Z, then the localization of A on the base is the pro-representing object for the non-commutative deformations of that fibre. And if I restrict F over Z, that gives me the universal sheaf of those deformations. And as before, there's a caveat that the algebras are related by Morita equivalence, and the sheaves in this case are additively equivalent. So sums of sums. Now, the application to autoequivalences. No. Okay. The construction. Right. But the construction is a natural global version of the construction of A. So there exists now a vector bundle on X so that I can take its relative endomorphisms over Y. So the sheaf endomorphisms on X push down to Y, and that's a sheaf of algebras on Y. And if I look at modules over that, then that's derived equivalent to X. And it can be shown under these assumptions that the relative endomorphisms are in fact just endomorphisms of the pushdown. So that's an algebra on Y with this ideal sitting inside it. So if I look at sections of that sheaf such that locally at each stalk they factor through the structure sheaf of Y, I should say some number of copies of the structure sheaf of Y, then that gives a two-sided ideal. We quotient by that, and we get the sheaf of contraction algebras, this A. I won't say how F is induced, but under these assumptions, so we want F to be crepant, some assumption on singularities of Y, so I want them to be hypersurfaces in the complete local rings on Z in Y, and some extra conditions that A is Cohen-Macaulay and F is perfect. I should note, in fact, if the codimension is 3 or more, these last two conditions are automatic. But in this case, there exists a symmetry of the derived category of X, and it's again given by a twist now of the sheaf F considered as the family over A. So, I mean, more precisely, F is an A module. So, right. So this should be compared to the work of Bodzenta-Bondal that I mentioned, which applies in this case, at least if the fibers are curves. And in that example I gave before, so with Ed Siegel, I previously worked on the autoequivalences of that derived category and produced some autoequivalences. So it's not clear that this gives the same. So it'll be interesting to compare, because this autoequivalence seems to be canonically associated to the contraction F. So now, last slides. It's tempting to speculate that it would be possible to lift this assumption on having a tilting bundle by working in the DG world somehow. So if I took a generator of the derived category, possibly with higher endomorphisms, then I could produce a DG version of this sheaf of algebras A, and then do the same construction. That would be very interesting to me. And we have this more general conjecture that curly A might recover now the complete local neighborhood of of Z in Y. So if I at least have curved fibers, then A would cover Y localized along Z. And that's all I had to say. Thank you very much.
Questions?
The A infinity augmentation of A related to this DG algebra thing that you're looking at?
I should say that DG algebra, I don't know what I'm looking at yet. That's pure speculation. No, it's in a different direction. It's in a different direction. So that A infinity algebra is given by expressing A as the endomorphisms of some object in the category of singularities. So it's the minimum model of the DG algebra associated to that. So it's in a different direction to that final speculation.
If no more questions, I thanks Will again.